So hello everyone, this is Dr. Nimish Kumar Srivastava in today's video lecture of optical communication, that is having a code of KOE 03058. So in this we are going to discuss about the eye diagram, the basic concept related to the eye diagrams. In our last lecture we have discussed about the coherent detections, what are the different types of, what are different configurations in which we can do the coherent detections. We saw that it can be done in the homodyne as well as in the heterodyne detection modes. Apart from that, we have seen that why we are using coherent detections, because it leads to improvement in the signal to noise ratio. In comparison to the direct detections that we were using, that means intensity modulation with direct detections, we saw that it was suffering from a low signal to noise ratio. So in order to improve that signal to noise ratios, the coherent detections were started using after the disadvantages that arises in the intensity modulation with direct detections. So now we will see about the concept of a eye diagram. So in the eye diagram we can see that it is basically used to just evaluate the effect of intersymbol interference on the received signals. So if you want to analyze what is the effect of intersymbol interference on the received signal, then we have to switch to the eye diagram. This eye diagram can be easily, with the help of this eye diagram, we can visualize that what is the effect of noise on the incoming signal. That means what is the effect of jitter, as well as what is the effect of intersymbol interference on the received signals. So in this eye diagrams, this eye diagram is basically a very powerful measurement tool for assessing the data handling ability of a digital transmission system. So this method has been used extensively for evaluating the performance of a wired lines system. That's why we are using it for the optical fiber data links. So in this eye diagram features, we can easily find what is the effect of intersymbol interference on the received signals. So in this diagram you will see that there are two terms that is associated. Your entire figure is going to be have a boundary, that is P on and P off. P off is basically assigned to a bit 0 and P on means bit 1. That means we are transmitting our entire data bits in between zeros and ones. Information is transmitted in the form of zeros and ones. So we will see that B off going to indicate that it is now 0 and B off it is now 1. So that diagram is easily visualizing the term B off. So we can easily see that this one is B off and this is B on. So at this level we are getting bit 1 and at this level we are getting bit 0. So that is the thing which is indicating the reception of a proper bits, because the information is in the form of series of zeros and ones. So whatever the things that is at this point, it is 0 0 and at this point this is bit 1. So we can easily see that things. So in this figure shows that this display pattern shows that eye pattern, and the upper and the lower bands are determined by the logic ones and zeros shown by B on and B off respectively. Now this is one. In this case there are various things that can be visualized. Now before moving into details about this, let us try to visualize the thing that how we are drawing this eye diagram. So in that content, let us try to take the example. So suppose that I am having a NRZ bit pattern having a series of zeros and ones. So this is bit duration TB, 2 TB, 3 TB, 4 and 5 TB. This is time and this is NRZ waveform. So in this, what is happening? Suppose that we want to transmit zeros and ones. So this will be indicated by high, then for 0 it will be indicated by 0, and again 1, then 0, then again going to high, and finally it will move to this point. So this is the NRZ encoding that is done at the transmitter side. So whenever this signal is received, so obviously that this signal is not going to be received as ideal as in this case. So it will be not like a complete a square pattern. There will be some change in the values. Now that change in the values is arising because of some noise that get introduced inside the signal. So suppose that because of the effect of noise, some fluctuation start going to surpassing the strength of the signal. So in this case, suppose if I am considering it as an ideal, so this I pattern is drawn by overlapping the series of zeros and ones that we are transmitting. So now in this case, we are considering 1 and 0 pattern. So this is high, so this is high and this is low, and we are overlaying all these zeros and ones in order to get the original I diagram, to get the strength of this received signal. Now suppose that now some noise start introducing in the signal and we are getting some fluctuations like this. So instead of a complete or a perfect square, now it is something like this. It is something like this. Like this. Now, as a result of this, this thing has to be superimposed on this one also. Like, so this was our origin 0 and our value 0. This is 0, this is 1, and this is -1 for 0 term. Now for this, we can see that for the duration TB, the signal is moving something like this, and for duration 0 to TB, I mean TB to 2 TB, the signal is moving something like this. Again for 2 TB to 3 TB it is high, but the pattern is something like this. And for this duration also the pattern is something like this. Again for 4 TB to 5 TB it is something like this, right? So in this way, when we are overlaying the incoming zeros and ones bit pattern, so it will give us to a figure which is resembling something like a I. Now this is your, if you are just getting the distance from at the center of the eye opening, that is the spread of the eye, and similarly the width, this eye pattern is having a width like this way. This, the wider your eye is, the lesser will be the effect of the intersymbol interference, and the moment your intersymbol interference start increasing, the slope of this pattern going to decrease. Like if suppose that I am having this pattern something like this, so it is having a slope, right? So now with the increase in intersymbol interference, it will start decreasing like this, and again this way. So the moment it get decreased, your eye opening, the opening portion of the eye will decrease to such a level that it won't be that the person sitting at the receiver side won't be able to distinguish between whether the symbol that has been transmitted from the transmitter is 0 or 1 with this strength of the slope. Now this strength of slope decreases, or the value of a slope decreases because of the intersymbol interference. So we have to keep this all thing in our mind about the eye diagram. Now, so this is the way in which we draw the, this is 1 and this pattern shows the -1. So this is the eye diagram that by combining which we can get this figure. So in this way, this is the boundary between that which if the strength if the strength is in between this one, we say that that is for the bit 0, and similarly this is the margin that is set up for the considering a bit as a 0. So here it is 1, here it is 0. Now this is the threshold level for the determining whether the bit pattern strength comes under the 1 category, high level, or comes under the low level category. So above this value something can be treated as a 1, and below this value something can be treated as a bit 0. So maximum signal voltage will be this portion and the minimum is this one, right? And the slope of this line going to give us the sensitivity of the timing error, sensitivity to timing error, because timing error also arises because of this noises or jitter. We say that the problem that is your jitter. So because of the jitter, the sensitivity start decreasing, because your noise it start enhancing in the it will start interfering the strength of the signal. As a result of that, the slope will decrease and it will now something like the width or the spread of the eye will be very less. So as a result, this gives to a decrease in the sensitivity of the receiver, and this time interval over which a signal can be sampled is something given by this width, right? And the best sampling time for the signal to get the signal back is this point at which the opening of an eye is maximum. So we have to keep this point at what receiver, that at what point the sampling time is best to get the best recovered to recover the signal in a best strength and the distortion at a 0 crossing. So this is the distortion at the 0 crossing. The distortion also introduces in the inside the series of bits and series of zeros and ones, and the width of an eye opening defines the time interval over which the received signal can be sampled without having some error, or without having some error due to the ISI problem, that is intersymbol interference. That width of eye gives you the time interval over which the received signal can be sampled without error, like this one, this width of eye. Similarly, the best time to sample we have already understood, which is the best time to sample. This the time at which the opening of an eye is maximum is the best time to get the sample. So the best time to sample the received signal waveform is when the opening of an eye is largest. That means the height. This height is reduced as a result of a amplitude distortion in the signal. The moment amplitude distortion is now inculcating in the signal, the strength of the signal decreases, which leads to a reduction in the height of a eye. So the vertical distance between the top of the eye opening and the maximum signal level gives the degree of distortions. The more the eye opens, or the more the eye closes, the more difficult it will be for a receiver, for an instrument to distinguish between 0 or a 1. Right? So the height of the eye opening at a specified sampling time shows the noise margin or the immunity to noise. What is the noise margin? The noise margin is the percentage ratio of the peak signal voltage V1 for an alternate bit sequence defined by the height of the eye opening to the maximum signal voltage V2, which is measured from the threshold level. What was the threshold level? The level that we are considered at the center of the eye, like this one. This is the threshold level. Now, This ratio is your noise margin, that is V1 upon V2 gives the noise margin, and the rate at which the eye closes as the sampling time varied, that is the slope of a eye pattern. The slope of a eye pattern decides the rate at which the eye closes as the sampling time interval is varied, is something given by this slope. So which further determines the sensitivity of the system to the error that arises due to the time. So the possibility of timing error increases as the slope becomes more and more horizontal. The moment it is becoming more and more horizontal, the point at which it becomes more horizontal, it would be difficult for the receiver to distinguish between the 0 and 1. Now the next thing is about the timing jitter, which is also referred to as a phase distortion. In the optical system, this timing jitter arises from the noise in the receiver and the pulse distortion in the optical fiber. We have this in the photodetector. We will see that what are the various kinds of a noise which is associated with the photodetector. That is short noise, dark noise, as a thermal noise. We will see in details what are those things and how it is affecting the performance of the system. Now the case is that the excessive jitter can result in a error in the bit. So since such jitter can produces uncertainties in the clock timing, and the moment clock timing is not perfectly matched, synchronization is not there, so obviously there will be a problem in getting the accurate signals or recovering back our original signal. So this time uncertainty will cause a receiver to lose synchronization with the incoming bit stream, thereby incorrectly interpreting zeros as 1 or 1 as zeros. So if the signal is sampled in the middle of the timing interval, that is a midway between the times when the signal crosses the threshold level, at that time the amount of distortion at the threshold level going to decide the amount of jitter. This timing jitter is given by a formula which is your del t upon Tb. Tb is the 1 bit duration. We have discussed in this figure also, whenever we are transmitting a series of zeros and ones, so that is your time Tb, 1 bit pattern or 1 bit duration. Now in this, Tb is 1 bit durations. So what is happening? This rise time, now the two things there, rise time and the fall time. What is the rise time? The timing, the time that a system require to move from the 10% to the max 90% of the final amplitude. That is the time which can be considered as the rise time. So the more distinct form is the between 20 to 80% rise time, and we can see it from this diagram, that from here, this one. So this is the rise time from 20% to 80%. This time is your rise time, time taken by the signal to move from 20% to 80% of the maximum amplitude. So that is telling us our rise time. And similarly the fall time, whenever your the time that is required by the system to generate a signal which is falling from a 80% of the maximum value to the 20% of that value. So that is your fall time. That means point from here, we have considered this point as and this point. So this is your fall time. From here it is 80% to move down to a 20%, this comes under the fall time period, and if we are moving from 20% to the 80% of the maximum strength, it will fall under the rise time. So in this way one can determine the strength or the health of your signal that is received, whether the signal is proper or not, if signal is matching with the signal which is sent by the transmitter side or not. The opening of an eye, the width of an eye going to give us the correct information about whether there is a proper synchronization in the clock timing or not, whether the noise effect is enhancing, the noise effect has overpassed the strength of the signal or not, whether the jitter is in the signal or not. So we will get all these information with the help of this eye diagram. So now the next thing is about the, once we got through the basic overview about the eye diagram, the next important point is what are the various kind of detectors that can be used in the optical communications. We have discussed the sources that can be used for generating the optical signals, that is LED and laser. Now the next thing is that once you have transmitted the signal, generated a photons or optical signals, pass it through a transmission medium, then on the receiver side also we need to detect back the original electrical signal from the photons. So that device is called as a photodetectors, which is converting back the optical signal into its equivalent electrical strength. So that is done by a photodetector. So in this photodetector, we will see the working principle of the photodetector, how photodetector is operating. Like in the case of LED, we saw that LED is operating in the forward bias mode. In the case of detector, we will see that detector is going to operate in the reverse bias mode. So how that reverse biasing going to affect the performance of the system, how it is detecting the photons, and in which area it's going to detect the number of photons that is going incidented on the receiver on the depletion portion. So in the case of LED also, we saw that the main portion which is responsible for the generation of the photons is your depletion width, right? So in the depletion width, the recombinations is occurring, and that is the electron is falling back from the conduction band to the valence band, and as a result of which photons going to be generated because of the diode band gap semiconductor. But in the case of this photodiode, what is happening? In the case of photodiode, we are biasing the PN junction in the reverse bias mode. We have biased the PN junction in the reverse bias mode. So in this case, the moment, suppose that we have not provided any biasing to this circuit, and before biasing, due to the process of the diffusions, a depletion layer will be formed, and after that, if we are applying a reverse bias voltage, so because of the application of a reverse bias voltage, whatever the magnetic carriers which is present inside the depletion layer will be that they are set apart from each other, right? So in this way, the charge carrier will now start moving away from each other, and they will do what? They will just increase the width of the depletion layer, and as a result, the charge will now start moving. If it is in this way, electron, this is your electron and this is your hole. So hole, what is going to affect on the hole? Hole will start moving in this direction because of the presence of the applied voltage which is negative, and the electron will start moving in this direction because of the attraction done by the positive charge or positive bias. So as a result of this, those charge carrier is swept apart from each other, and a small current will start flowing inside the circuit. So that is the complete process of a photodetector. In the case of a pin, what we are doing, as we know that the main portion which is responsible for increasing the conductivity, increasing the generating the electrical equivalent, is your depletion width. So the moment you are widening the depletion width, the more the charge carrier will be get depleted, and it will move away from each other. As a result of this, a current start flowing in the photodetector. Now this is the very basic principle responsible for this pin photodiode. In our next class, we will see which material that can be used for this eye, which is an intrinsic layer. Apart from that, what are the various drawbacks because of which we are now going to introduce the another type of photodetector, which is the APD, called as the avalanche photodetector. We will see all those things in our detail in our next class. So that's all for today. Thank you all.